Okay, so in the last series of videos, we talked about the gas laws, all but one gas law. We have one more gas law to go over, but we went over the gas laws regarding volume. So the ones in blue are the gas laws about volume. So there's the Boyle's law and the Charles's, and the Avogadro's law. And then we have the law relating pressure and temperature to each other. So here's the one in green is the pressure and temperature, and that's Gay-Lussac's law. And then we have the combined gas law, which smooshes the Boyle's law, Charles's law, and Gay-Lussac's law all together. So as you can see here in Boyle's law, we have the P times the V. P times the V equals P times the V. The original pressure and volume multiplied by each other equals the resulting pressure and volume, the new pressure and volume. And that's what we have in the combined. It's pressure P1 times V1 equals P2 times V2. And then for the Charles's law, we have the volume over the temperature. So V1 over T1 equals V2 over T2. And we also can see that in the combined gas law, V1 over T1 equals V2 over T2. And then for Gay-Lussac's law, we see the pressure divided by the temperature. P1 over T1 equals P2 over T2. And we can see that in the combined gas law as well. There's P1 over T1, P1 over T2. So the combined gas law smooshes these three laws together into one math formula. But you might be saying, well, what happened to Avogadro's law? Avogadro's law was just left out there lonely. Nobody included it in the combined gas law. Well, Avogadro's law is added into well, it's not added, it's factored into the ideal gas law. So as you can see, the combined gas law would be P times V over T. The ideal gas law also includes Avogadro's law, the N, which is the number of moles of the gas. So N stands for the number, N for number of moles of the gas. So P times V equals, or P times V divided by N times T equals this constant. Now, this is what's really cool about this is because you take any gas, hydrogen, helium, any gas, and you take its pressure times its volume divided by the number of moles of that gas times the temperature in Kelvin, and you will always get this number, 0.0821. Always, 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 you will always get this number. And the units of measurement for that is atmospheres times liters divided by moles times kelvins. And as you can see, this pressure, the pressure is in atmospheres, the volume is in liters, the number of moles is in number of moles, and the temperature is in kelvins. So of course you're going to get a unit of measurement, atmospheres times liters over moles times kelvins, because that's what the formula is made of, atmospheres times liters divided by moles times kelvins. So this is an easy way, I bring that up because it's an easy way to remember the units of measurement of this gas constant is just knowing that it's P times V divided by N times T. So atmospheres times liters divided by moles times kelvins. And that's 0.0821. And yes, you do have to memorize this for your chemistry classes. Most teachers make you memorize it. So I would count on just having to memorize this 0.0821. So we're going to call this constant R. So the constant is going to have the letter capital R stand for it. So that makes this P times V over N times T equals R. So you can rearrange that algebraically. If you want to get rid of this NT on the bottom of the PV, you can just multiply both sides by N times T, and these will cancel each other out on this side, and you will end up getting PV equals RNT. Or as you will commonly see it, PV equals nRT. I don't know why people rearrange the N and the R because mathematically it doesn't matter. It doesn't change your answer. But people usually put it down PV equals nRT. Um, I think just because nRT is alphabetical. But it's the same thing. It's PV divided by NT equals R. And I just wanted to show you um, this original way of writing it, the PV divided by NT, because I wanted to show you where it came from, that it came from the combined gas law and Avogadro's law, gas law. So, because it has the N in it. So I just put the PV over NT so I could show you where this formula came from. But you're mostly going to see it as PV equals nRT. It's the same thing. And that R is always going to be 0.0821 atmospheres times liters over moles times kelvins. So this is always, always, always going to be R, what R is. This doesn't change. So let's try a problem. This says, at what temperature would 2.10 moles of N2 gas, of nitrogen gas, have a pressure of 1.25 atmospheres and in a 25.0 liters tank? So at what temperature, this asks the question at the beginning of the sentence, at what temperature? So it's the temperature that we're going to be looking for. So temperature is our question mark. And that's going to be in kelvins, because temperature has to be in kelvins for dealing with gas laws. At what temperature would 2.10 moles of nitrogen gas, so the 2.10 moles would be the N, because N stands for the number of moles. So N is going to be 2.10 moles. At what temperature would 2.10 moles of N2 gas have a pressure of 1.25 atmospheres? So our pressure is going to be 1.25 atmospheres, and in a 25.0 liter tank. So that's going to be, it's liters, so that's going to be our volume. So 25.0 liters. Those are going to be our factors when we do this problem, when we work this problem. So if we use the ideal gas law of PV equals nRT, or as I put it up here on the left, PV over NT equals R, that's the original formula, but we converted it into PV equals nRT just because this is how you're normally going to see it. So we're looking for T in this. Our question mark is for the temperature. What temperature in kelvins is all of this going to take place? So since we're looking for temperature, we need to isolate T and get it on one side of the equal sign all by itself. So in order to do that, we are going to divide both sides by N and R. So we're going to divide both sides of the equal sign by N and R. So this N and R cancel each other out on this side, and all we're left with is T. And then we have PV over NR over here on this side. So we're going to have PV divided by N times R equals T, the temperature, because that's what we're looking for. That's our question mark, is temperature. So if we set it up and we plug in the numbers this way, PV over NR, we're going to get 1.25 atmospheres times 25.0 liters divided by 2.10 moles times our gas constant 0.0821 atmospheres times liters over moles times kelvins. And that's all going to equal T, the temperature in kelvins. And I'll put kelvins by here, meaning it's kelvins is what we're measuring the temperature with in this formula. Now, if you look at these units of measurement, you can see that the atmospheres up here cancels out with the atmospheres down here. The liters up here cancel out with the liters down here. The moles right here cancel out with the moles down here. And that leaves us just with kelvins, which is going to be what we're looking for, what the question mark is all about. What is how many kelvins? So we know we've set this up right because the units of measurement cancel out really nicely. So now all we have to do is multiply this thing, 1.25 times 25.0 all over 2.10 times 0.0821. And that's going to give us the temperature in kelvins. So this is going to be 31.25 divided by 0.17241. So that's going to equal 181.2539875877 kelvins. Now, since we have three significant figures in all of these numbers that we're dealing with, we know we're going to round this to 3 sig figs. So 181.253987, that just rounds to 181. So 181 kelvins is the answer to this problem.